Every single day, over 300 million servings of instant noodles are consumed worldwide, making it one of the most popular convenience foods on the planet. A single modern processing plant can produce up to 5 million packages in 24 hours. With automated systems mixing, rolling, cutting, steaming, frying, and packaging noodles at speeds reaching 400 packages per minute. These factories transform raw wheat flour into shelf-stable meals that can survive months in storage, rehydrate in just 3 minutes with boiling water, and cost less than 50 cents per serving. But how do industrial machines create those distinctive wavy noodle blocks with such precision and consistency? What journey does wheat take from agricultural fields in the American heartland to become one of the world's most consumed processed foods? And how has a Japanese invention from the 1950s evolved into a $25 billion global industry feeding billions of people? Welcome to AgriCraft, where we explore the real stories behind your food. All will be revealed in this video. The story of instant noodles begins in post-war Japan, where a Taiwanese entrepreneur named Momofuku Ando observed people waiting in long lines for hot noodle soup at food stalls in 1957. Recognizing the need for convenient, affordable food in a nation recovering from wartime deprivation, Ando spent a year experimenting in his backyard shed to create noodles that could be stored for long periods and prepared quickly at home. His breakthrough came when he discovered that flash frying noodles in hot oil not only created tiny pores throughout the noodle structure that allowed rapid rehydration, but also removed moisture that would otherwise allow bacterial growth and spoilage. He introduced chicken ramen in 1958, packaging it in distinctive cellophane wrappers and marketing it as a revolutionary instant meal. The product initially cost 6 times more than fresh noodles but offered unprecedented convenience. The innovation spread rapidly, with instant noodles reaching South Korea by the early 1960s, then expanding throughout Asia and eventually worldwide. The global instant noodle market has exploded since those humble beginnings. Today, approximately 118 billion servings are consumed annually, with China leading consumption at over 46 billion servings per year, followed by Indonesia at 13 billion, India at 7 billion, Japan at 6 billion, and Vietnam at 5 billion. The United States consumes approximately 5 billion servings annually, making it a significant though not dominant market. South Korea holds the distinction of highest per capita consumption with nearly 75 servings per person per year, followed by Vietnam at 57 servings per capita. The industry is valued at over $25 billion globally, with major producers including Nissin Foods, Indofemi, Master Kong, Nongshim, and Maruchan operating massive production facilities across multiple continents. American agriculture plays a crucial role as a primary supplier of wheat, the foundational ingredient in most instant noodles. The journey begins not in factories but in wheat fields across the Great Plains, Pacific Northwest, and other wheat-growing regions of the United States and Canada. Wheat destined for instant noodles requires specific characteristics that differ from bread wheat or pastry wheat. The ideal varieties are hard white wheat or certain hard red wheat cultivars with protein content typically ranging from 10 to 13%, providing the gluten strength necessary for noodle texture while avoiding the darker color that whole wheat would impart. Seed selection happens through breeding programs that develop varieties combining high yield potential with quality traits, including appropriate protein levels, good milling characteristics, disease resistance, and adaptation to regional growing conditions. The cultivation of wheat follows agricultural cycles established over centuries but increasingly enhanced by modern agriculture technology. Wheat is classified as either winter wheat planted in fall and harvested the following summer or spring wheat planted in spring and harvested in late summer or fall. Winter wheat dominates production in states like Kansas, Oklahoma, and Texas where cold stratification improves yields. Spring wheat prevails in northern states including North Dakota, Montana, and Minnesota where harsh winters would kill fall-planted crops. The fields are prepared through tillage or increasingly through no-till methods that preserve soil structure and reduce erosion. Planting happens using precision seed drills that place seeds at controlled depths and spacing, typically aiming for densities of 1 to 1.5 million plants per acre. Environmental requirements for successful wheat cultivation include well-drained soils with pH between 6 and 7, Adequate moisture, particularly during germination and grain filling stages, and temperatures that allow gradual maturation. Wheat is relatively hardy and adaptable, but optimal yields require careful management. Fertilization provides nitrogen, phosphorus, and potassium based on soil testing, with nitrogen being particularly important for achieving target protein levels. Too little nitrogen results in low protein, unsuitable for quality noodles, while excessive nitrogen can cause lodging where plants fall over before harvest. Modern precision agriculture uses GPS-guided applicators and variable rate technology to apply fertilizers at optimal rates across fields with varying soil characteristics. Early care includes monitoring for pests and diseases. Wheat faces threats from insects including Hessian fly and aphids, fungal diseases like rust and mildew, and weeds competing for resources. Integrated pest management combines resistant varieties, crop rotation, and targeted pesticide applications only when economic thresholds justify treatment. Herbicides control weeds that would reduce yields and interfere with harvesting. The management practices aim to produce clean grain meeting food safety standards for human consumption, as instant noodle production requires exceptionally clean wheat, free from contaminants, toxins, or excessive foreign material. Harvest timing is critical and determined by grain moisture content and kernel hardness. Wheat is ready when moisture drops to around 14% or below, kernels are fully developed and hard, and the plants have turned golden and dried down. Modern combine harvesters cut the wheat stalks, separate grain from chaff and straw through threshing and winnowing processes, and collect the grain in onboard hoppers. A single large combine can harvest over 50 acres per day, processing the wheat as it moves through the field. The harvested grain must be transported quickly from combines to storage to prevent spoilage. Farm trucks haul wheat to on-farm storage bins or directly to grain elevators, commercial facilities designed for receiving, storing, and shipping grain. Transportation to processing facilities begins at these grain elevators, where wheat is tested for quality parameters including protein content, moisture level, test weight indicating kernel density, and presence of damaged kernels or foreign material. Only wheat meeting specifications is purchased for food use, with off-grade wheat diverted to animal feed. The wheat is loaded into rail cars or trucks for transport to flour mills, the first stage of industrial processing. The United States has extensive rail and barge networks optimizing grain transportation from rural production areas to urban processing centers or export terminals. The flour mills, where wheat becomes the foundational ingredient for instant noodles, are marvels of food processing technology. These facilities receive wheat in bulk, unloading rail cars or trucks using pneumatic systems that vacuum grain into receiving pits. The wheat first passes through cleaning systems employing screens, aspirators, and magnets, removing straw, dust, stones, metal fragments, and other foreign material. The cleaned wheat then undergoes tempering or conditioning, where water is added to bring moisture content to optimal levels for milling, typically 15 to 16%. This moisture softens the bran coating around the kernel while toughening the endosperm slightly, allowing cleaner separation during milling. The wheat rests for 12 to 24 hours in tempering bins, allowing moisture to penetrate evenly. The actual milling process uses roller mills, massive industrial machines with pairs of steel rollers turning at different speeds to gradually break wheat kernels and separate components. The first break separates bran from endosperm, with the coarser particles sifted into different streams using plansifters, large multi-deck sifters enclosed in cabinets shaking at controlled frequencies. The process continues through multiple stages of grinding and sifting, progressively reducing particle size while removing bran and germ to produce refined white flour. A modern flour mill might contain 40 or more individual grinding and sifting steps, each removing specific particle size ranges. The final flour for instant noodles is typically very fine, passing through screens with openings measured in micrometers, creating the smooth texture desired in noodles. Quality control at the flour mill includes continuous testing of flour for protein content, ash content indicating mineral levels from bran contamination, moisture content, color, and functional properties including water absorption and gluten development. Only flour meeting strict specifications proceeds to noodle factories. Many large instant noodle manufacturers operate their own flour mills, maintaining complete control over this critical input. Others purchase flour from commercial mills under contracts specifying exact quality parameters. The instant noodle processing plant is where agriculture meets advanced food processing technology. These facilities are enormous, often covering hundreds of thousands of square feet and operating continuously 24 hours daily. The production begins in mixing rooms where precise quantities of flour, water, salt, and alkaline salts, typically sodium carbonate and potassium carbonate, are combined. These alkaline salts, or Kansui, are essential for authentic noodle texture and the characteristic yellow color, affecting gluten development and creating the firm, elastic texture desired. The ingredients are measured using automated systems ensuring consistency, with typical formulations around 100 pounds of flour, 30 to 35 pounds of water, 1 to 2 pounds of salt, and smaller amounts of alkaline salts. The mixing happens in large industrial mixers using horizontal ribbon or vertical spiral configurations that blend ingredients into a crumbly dough over 5 to 10 minutes. Unlike bread dough that is smooth and elastic immediately, noodle dough at this stage resembles coarse meal or damp breadcrumbs. This crumbly texture is intentional as it allows for the next critical step. The dough is fed into compound rolling machines, massive pieces of equipment with multiple pairs of rollers that progressively compress and roll the dough into continuous sheets. The first pair of rollers receives the crumbly dough and compresses it into a rough sheet, perhaps 1 inch thick. This sheet immediately passes through additional roller pairs, each gap slightly narrower than the previous, gradually reducing thickness while elongating and aligning gluten strands. The process typically involves 4 to 8 rolling stages, reducing the sheet from 1 inch to a final thickness of approximately 1 to 1.5 millimeters. Between some rolling stages, the dough sheet is folded back on itself and passed through again, a technique that further develops gluten structure and creates the layered texture contributing to noodle chewiness. Conveyor belts transport the dough sheets between rollers and to subsequent processing steps. The continuous sheet emerging from the final rollers feeds directly into cutting machines equipped with rotating blades spaced to create noodle strands of desired width. Round noodles pass through circular cutting dies while flat noodles use straight blades positioned at specific intervals. Common widths range from 1 to 3 millimeters. The cutting speed is synchronized precisely with the sheet feeding rate to prevent tearing or bunching. The freshly cut noodle strands drop onto conveyor belts that create the distinctive wave pattern of instant noodles. The conveyor receiving the noodles moves slower than the cutting speed, causing the strands to bunch and fold into waves. This waving serves both aesthetic and functional purposes, allowing the noodles to pack efficiently into blocks while creating surface area that facilitates rapid rehydration during cooking. The waved noodles then pass through steam chambers where they are steamed at high temperature, typically around 200 to 212 degrees for 1 to 5 minutes. This steaming gelatinizes the starch, essentially pre-cooking the noodles so consumers need only rehydrate them rather than actually cooking from raw. After steaming, the noodles proceed to the defining step that makes them instant noodles, frying or drying. The traditional method still used for most instant noodles worldwide is flash frying in palm oil or other vegetable oils heated to between 280 and 310 degrees. The steamed noodles are portioned into individual serving size blocks and dropped into the hot oil where they fry for 1 to 2 minutes. The intense heat causes remaining moisture to flash into steam, creating the porous structure throughout each noodle strand. The oil temperature is carefully controlled because too low results in soggy, oil-saturated noodles while too high carbonizes the exterior before the interior dries. Automated frying systems use continuous fryers where noodle blocks move through hot oil on mesh conveyor belts, ensuring consistent frying time and temperature for every block. After frying, the noodles emerge containing around 3 to 8% oil by weight and 2 to 5% moisture, conditions that prevent microbial growth and provide shelf stability. The hot noodle blocks pass through cooling tunnels, where air circulation reduces temperature to safe handling levels, while allowing additional moisture evaporation. Non-fried instant noodles follow an alternative path using hot air drying at temperatures around 160 to 180 degrees for 40 to 60 minutes. This method produces noodles with much lower fat content, appealing to health-conscious consumers, but the drying time is much longer and the texture differs slightly from fried versions. Both fried and non-fried noodles undergo quality inspection where automated vision systems or human inspectors examine each block for proper color, shape, moisture content, and absence of defects. The dried noodle blocks then enter packaging lines, some of the fastest and most complex automated systems in food manufacturing. The noodles are first placed into primary packaging, either plastic or foam cups for cup noodles or plastic film for packet noodles. For packet noodles, the blocks are positioned in forming stations where film unwinds from large rolls and is formed into pouches. The noodle blocks drop into these pouches along with seasoning packets containing powdered soup base, oils, and sometimes small packets of dried vegetables or sauce. The pouches are sealed using heat-sealing bars that melt the plastic film, creating airtight seals, then cut from the continuous film. These steps happen in rapid succession, with some production lines achieving speeds of 400 packages per minute or higher. Cup noodle packaging involves different machinery where pre-formed cups arrive on conveyor belts, receive noodle blocks and seasoning packets, and then have lids applied and sealed. The cups may be shrink-wrapped in plastic film and packed into shipping cases. Throughout the packaging process, metal detectors and check weighers ensure that no foreign objects contaminate packages and that each meets target weight specifications. Labeling happens simultaneously with packaging, as film or cups are pre-printed with product information, nutritional facts, cooking instructions, and branding, or labels are applied separately using high-speed labeling machines. Quality control extends beyond visual inspection to comprehensive testing programs. Samples from each production batch are retained and tested in laboratory facilities where technicians verify moisture content, fat content, salt levels, and sensory characteristics including taste, texture, and aroma. Microbiological testing confirms absence of pathogens and that total bacterial counts remain within safe limits. These tests take time, so product may be held in warehouse pending test results before being released for distribution. Hygiene standards throughout instant noodle factories are rigorous, with workers wearing protective clothing, facilities designed for easy cleaning, and regular sterilization of all equipment contacting food products. Food safety protocols follow HACCP principles, identifying critical control points where hazards could occur and implementing monitoring and corrective actions. Storage of finished instant noodles happens in climate-controlled warehouses, protecting products from heat, humidity, and pests that could degrade quality or contaminate packages. While instant noodles have shelf lives of 6 to 12 months, proper storage conditions maintain quality throughout this period. Temperature control prevents oil in fried noodles from becoming rancid, while humidity control prevents moisture absorption that could make noodles soggy or promote mold growth. The packaged noodles are stacked on pallets, shrink-wrapped for stability, and organized using warehouse management systems tracking lot numbers and expiration dates. Distribution channels move instant noodles from manufacturing plants through complex supply chains to retail stores and ultimately consumers. Major producers operate regional distribution centers, positioning inventory near major population centers, reducing delivery times and shipping costs. The products are transported by truck to wholesalers, grocery chains, convenience stores, dollar stores, and increasingly to warehouses fulfilling online orders. The logistics are optimized using sophisticated software modeling demand patterns and routing deliveries efficiently. Export markets are significant, with American-produced instant noodles shipping globally, while imported varieties from Asia line American store shelves. Reflecting the international nature of the industry, the pricing of instant noodles remains remarkably low despite complex manufacturing processes. Economy brands retail for 20 to 50 cents per package, while premium varieties might reach $1 to $3. This affordability results from economies of scale in massive factories, relatively inexpensive ingredients, and highly automated production, minimizing labor costs. The low price point makes instant noodles accessible to low-income consumers worldwide. Though this raises nutritional concerns as people may rely heavily on instant noodles as staple foods. Byproducts from instant noodle production are modest but managed carefully. Dough scraps from the rolling and cutting processes are typically reincorporated into subsequent batches, minimizing waste. Wheat bran and germ removed during flour milling are sold as animal feed or used in bran cereals and other human food products. Used frying oil from production is collected and often recycled into biodiesel production or used in animal feeds, preventing disposal problems and generating some revenue. Packaging waste, including film scraps and rejected packages, are segregated for recycling where possible. Culinary applications of instant noodles extend far beyond simple preparation with boiling water. While that remains the most common consumption method, creative cooks use instant noodles as ingredients in stir-fries, salads, soups made from scratch, and even desserts. The convenience and neutral flavor make them versatile. College students and budget-conscious households have developed countless variations, adding eggs, vegetables, meat, cheese, and other ingredients to enhance basic instant noodles. Some restaurants feature instant noodle-inspired dishes, recognizing cultural significance and nostalgia associated with these foods. The dried noodle blocks can be crushed and used as crunchy salad toppings or coating for fried foods. Nutritional value of instant noodles is controversial and varies by product. A typical serving contains 300 to 400 calories, primarily from refined carbohydrates in the wheat flour and fats from frying oil. Protein content is modest at 8 to 10 grams, coming mainly from wheat gluten. The sodium content from added salt and seasoning packets is very high, often exceeding half the recommended daily limit in a single serving. Micronutrient content is low unless products are fortified, which some manufacturers do by adding vitamins and minerals during production. The heavy processing and lack of fiber, vitamins, and phytonutrients found in whole grains and vegetables mean that instant noodles provide calories and satiety but limited nutritional value. Regular consumption as a dietary staple raises health concerns, including increased risk of metabolic syndrome, cardiovascular disease, and nutrient deficiencies, particularly among populations consuming instant noodles multiple times daily. Recognizing these concerns, some manufacturers have reformulated products to improve nutritional profiles. Non-fried varieties reduce fat content substantially. Whole grain versions increase fiber and micronutrients, though they represent small market shares due to higher costs and darker colors consumers find less appealing. Reduced sodium formulations address perhaps the most serious nutritional issue, though flavor adjustments can be challenging. Fortification adds vitamins A, iron, and other nutrients, meaningfully improving nutritional value, especially in markets where instant noodles comprise significant portions of diets. Environmental impact of instant noodle production includes several considerations. Wheat cultivation requires land, water, and agricultural inputs, including fertilizers and pesticides, though wheat is generally considered a relatively efficient grain crop. The milling and noodle production processes consume significant energy for operating machinery, heating oil for frying, and running climate control systems. Palm oil use in frying has faced criticism because palm plantations have driven tropical deforestation, though certified sustainable palm oil initiatives aim to address these concerns. Packaging waste is substantial given billions of packages produced annually, with plastic and foam cups creating disposal challenges, though increasing recycling and development of biodegradable alternatives offer improvements. Water use in factories and wastewater treatment are managed through modern treatment systems but still represent environmental footprints. Sustainability efforts in the industry focus on several areas. Energy efficiency improvements, including better insulation, heat recovery systems, and more efficient machinery, reduce electricity and fuel consumption. Water recycling systems allow factories to reuse processed water after treatment, dramatically reducing freshwater intake. Packaging innovations explore compostable materials, increased recycled content, and reduced material use through thinner films and optimized designs. Some companies are investigating cricket flour or other alternative proteins as additives to improve nutrition and reduce environmental impacts compared to traditional meat-based flavoring ingredients. Agricultural sustainability initiatives encourage wheat farmers to adopt practices, including precision fertilizer application, integrated pest management, and soil conservation, that maintain productivity while reducing environmental impacts. Looking at the complete journey from wheat seeds planted in American fields, where modern farming practices optimize yields and quality through mechanical harvest, using massive combines that efficiently gather millions of tons of grain annually, then transportation to flour mills, where industrial processing transforms wheat kernels into refined flour through precise grinding and sifting, and finally to instant noodle factories where automated systems mix, roll, cut, steam, fry, and package noodles at astonishing speeds. The supply chain reveals a mature global industry connecting agriculture with advanced food processing technology. The 118 billion servings consumed annually represent an industry that has democratized convenient food, making hot meals accessible to billions, including many living on minimal incomes. The production scale is staggering, with facilities producing millions of servings daily through processes optimized over decades. The transformation of simple wheat flour into complex foods with months of shelf stability and 3-minute preparation times demonstrates how food processing technology extends beyond preservation to creating entirely new product categories. From the essential role of American wheat farmers, providing the foundational ingredient through the remarkable efficiency of modern flour mills, processing thousands of tons daily, to the synchronized precision of instant noodle production. Lines where every second dozens of packages emerge ready for distribution. The instant noodle industry exemplifies industrialized food production at massive scale. While nutritional concerns merit attention and environmental impacts require ongoing mitigation, the accessibility and convenience that transformed instant noodles from post-war innovation to global phenomenon explain why they remain staple foods for billions worldwide. Thank you for watching this exploration of instant noodle production here on AgriCraft. If you found this journey from wheat field to factory floor informative, please hit the like button and subscribe to our channel for more deep dives into food processing technology and modern agriculture. Leave a comment below telling us your favorite instant noodle variety or questions about industrial food production. Until next time, keep exploring the remarkable systems behind the foods we eat every day.